Welcome to the geochemistry session. I'm Tim Glotch from Stony Brook. I hope the real geochemists in the room aren't too offended that I'm both chairing and giving a talk in this session. This is not a geochemist. So we have 3 talks here. Alberto Sal's our second talk. I think he will be calling in and presenting remotely. So I'm going to start my timer on myself now. So today I'm going to talk about a series of experiments we've conducted in collaboration with the IMPACT team out of University of Colorado. And what we're trying to do is understand a little bit better the process of space weathering. And to paraphrase Sarah Noble and Brett Denevi, if space weathering were a country, this would be our flag. It describes the processes that occur. And what we've done over the, actually almost exactly starting a year ago, is try to simulate the processes of micrometeoroid bombardment and solar wind implantation on a set of prepared, well-characterized samples, and then analyze those samples spectroscopically and using other techniques at a variety of spatial scales to see if we can start to piece together not which process is more important or which one dominates, but what are the relative effects of micrometeor bombardment and solar wind implantation, as well as these other processes on our samples. So, question, why do we want to do this? Well, we want to measure changes in chemical speciation and distribution of our samples that are using as proxies for lunar materials. And we want to do this primarily using X-ray absorption spectroscopy, which is great for telling us about chemical speciation, oxidation state, and structure, as well as transmission electron microscopy, which gives us the really, really fine scale detail. Then we want to use these measurements to inform the analysis and interpretation of visible near-infrared and mid-infrared spectra from target bodies in space. And we hope over time that this will improve our understanding of past and current processes acting on these surfaces. Okay, so our first step, I'm going to talk about 2 sets of samples. Some of them were bombarded by protons, others were dust impacted using, well, I'll get to that in a second, and some underwent both processes. We did our hydrogen bombardment experiments at Brookhaven National Laboratory's tandem Van de Graaff generator. Our protons coming out are a little bit higher than solar wind energies. They're 12 keVs, but this is about as low as we can get at Brookhaven. And we're using the source because it's right down the road from us and it's pretty convenient. Our initial tests were done at these conditions, and we end up with a total dose on our samples of about 10 to the 16 protons. And we estimate for the energy of these protons that the estimated depth of penetration is about 112 nanometers. We did our dust impact experiments at the Colorado Impact facility using their particle accelerator. These are our target samples. So here's an olivine, San Carlos olivine thick section before irradiation and impact. Here is olivine section post-impact. It has this kind of big color change, not necessarily because of the impact processes, because we did some gold coating for SEM afterwards, but you can kind of see the surface looks pretty messed up as a result of the impact as well. So for these impact experiments, our dust particles that we were using were made of olivine, so roughly the same material as our target. Those olivine particles were coated in a conductive organic polymer called polypyrrole, but it allows us to avoid using metallic projectiles, which some other investigators have done. Here are the statistics for our 2 samples. Here is our sample that has been irradiated before the impact experiments, and here's a sample after that has been not irradiated but impacted. Each sample was impacted roughly 10,000 times over a course of about a day. And what you're looking at here are the mass and velocity distributions. And so our velocities of our impactors were between about 1 and 10 kilometers per second, with a lot of these being a little bit on the lower end of that scale. For this first set of experiments that we did, we really just wanted to kind of open up the chamber and just throw every single particle that we could at it to see what would happen. our future experiments, we certainly want to more tightly constrain the velocity ranges to be more appropriate for lunar conditions. They're pretty close. I mean, that just means Mihai and Tobin know what they're doing. So here are just some reflected light images of the surfaces of these two samples. One sample, some surface area on the sample has been, it's been hit a little bit. It was a little off the center of the beam, so we're not right in the center of that beam, and it's been damaged but not incredibly damaged. Here is reflected light micrograph of, there we go, of a surface kind of right in the center of the dust impact beam, and you can kind of see how damaged and messed up it is. We can look spectroscopically at these materials in bulk, so the next few slides are going to be starting kind of at bulk scales and then progressively getting to finer and finer spatial scales. So here are just visible near-infrared spectra of our two samples. These are collected with our ASD field spec in the lab. So the black and gray samples are our pre-impact samples. After they have undergone impact, what you're seeing here now is in the pink and in the red. And so I'll just point out that we see some things that are consistent with what we'd expect from a space weathering process. We see an overall reddening of the slope down going in this direction. We see a decrease in albedo overall, and we see a dampening of the depth of the spectral features. We also see some organic signatures in there. That's due to that coating on our projectiles, which has then kind of become incorporated into our sample. Okay, we can do mid-IR spectroscopy at microscopic scales. To do this, we used our IN10MX micro FTIR at Stony Brook. The IR image you're looking at here is an image of the reflectance at this wavelength, which is about 926 micron wave numbers. What you're seeing here in blue is basically our unaffected pure olivine. This is a beautiful olivine feature right here in the 10 micron region. In these areas where you see in red and green, these are areas around craters that have formed. What you see is you still see the bulk of this olivine feature, but you see the shape of it has changed. What we're doing is, this is consistent with the idea that we have convolved the olivine spectrum with a more glassy material that we think likely formed by impact and probably vapor deposition. We also see some features out here at shorter wavelengths, which are consistent with the organic coating that that's been incorporated into the sample. I didn't mention that these data are acquired at a spatial scale of 25 microns per pixel. And so our craters are probably close to around 10 microns or so. So our craters are probably around less than 1 pixel, but you're seeing certainly damage in the area around these craters that is much more extensive than the individual crater itself. We can go down in spatial scale. This is data that was collected by my graduate student, Jordan Young. So here we're looking at micro Raman data, and these are at spatial scales of roughly 500 nanometers per pixel. We see a beautiful olivine Raman spectrum up top from this relatively undamaged area. When we go down and look at a more damaged area, we see the olivine peaks are still there, but we've induced a lot of fluorescence in the sample, which is often something that you see when you introduce amorphous material into a Raman spectrometer. We also see these D and G carbon bands here, which are due to the carbon that was in the projectile. But we're seeing both the damage and structural changes at kind of these variety of spatial scales, which is kind of the point here. Here are the first TEM data we got of these samples. So we got a fib section sliced through one of the craters. Some colleagues of ours at Stony Brook were kind enough to collect these data for us at the Center for Functional Nanomaterials at Brookhaven National Lab. Here's the underfocused image shows this the best, where we see this kind of rim that's maybe 20 or 30 microns thick of darker material with smaller, 3 to 5 micron sized blebs here. We see larger things further down the sample. I'm not quite sure what those are. These are, I'm not a TEM person, but this looks like the TEM data that Sarah and Lindsay Keller have acquired. We're going to do more work on this. We're sending these samples down to Rhonda Stroud and Kate Burgess at the Naval Research Lab for more kind of in-depth analysis, and their TEM is way better than the one that we have, so we're hoping that we'll get some a little bit better data. Okay, one of the challenges in trying to understand not just the structure, but the chemical speciation. So we want to understand the oxidation state of iron, particularly in these samples. One of the best ways to do that is with X-ray absorption spectroscopy. We do that at synchrotron facilities like the National Synchrotron Light Source 2. Now, when we do a typical X-ray absorption spectroscopy measurement, you have a thin section and you shine the X-ray beam through that, and then you collect the transmitted radiation on the other side. If we're looking specifically at iron, one thing that we have to be very aware of is that for any given mineral, when we're looking at this iron K edge, the attenuation depth, basically the depth to which we're sensitive with the X-rays, is on the orders of tens of microns, several tens of microns. And so if we're looking, say, for an oxidation state change in the very upper surface, that signal is going to be drowned out almost completely by the bulk sample. So we have a way, we think, to try to get around that. So here's just this in kind of graphical form. My postdoc, Sarah Nicholas, put these slides together. She's our X-ray spectroscopy expert. Well, if we care about this upper surface and this is the volume or the depth over which we're sensitive, then our signal that we care about is going to be drowned out by the bulk chemical signal of the sample. So what we're going to do is go to the Advanced Photon Source in Chicago. We're going to orient our thin sections and do grazing angle measurements. And these are measurements where we do the X-ray absorption spectroscopy with an incidence angle much, much less than 1 degree. Here we can be sensitive only to the top 100 or so nanometers of the sample, and we should be able to get a really precise and accurate measurement of the change in oxidation state of the upper layer of our sample after both irradiation and impact. All right, so everything I've talked about for the last 12 minutes now, I'll finish up, was done on 2 samples, and it was kind of a trial run. Our next steps, which we're doing right now, is we're preparing for several different minerals, 8 identical thin sections that will be oriented to a specific orientation, so that we're, for each of our experiments, we're comparing apples to apples to apples to apples to apples to apples to apples. And we're going to do a series of experiments, one of which we're going to just leave alone. We're going to have one sample that we only irradiate with protons, one that we only impact with dust, one that we irradiate with a laser to simulate the dust bombardment, one that we do protons and dust, one that we do protons and the laser, and one that we do laser and the protons in that order. And so the idea behind these experiments is then to try to disentangle the order of operations, if that matters. I'm not sure that it does, but we'll get a sense of how well the laser experiments simulate the actual dust impact. Those are experiments that have been done for a long time, and we can kind of move forward there. So to summarize, these 2 samples that I've just described result in structural, mineralogical, and spectral changes at basically every spatial scale that we looked at. The chemical speciation and structure as a function of depth are probably the most challenging data to acquire. We have our first set of beam time coming up later this fall, which we're very excited about, and probably see Sarah presenting that at LPSC, I would imagine, or AGU coming up. One thing we'll also do moving forward with our colleagues at the Naval Research Lab are TEM and EELS, electron energy loss spectroscopy, which will allow us to get information on oxidation state and crystallinity at several nanometer spatial scales. All right, with that, I will end, and I left myself about a minute or so for questions. So, thank you. Tom.
Really nice talk. So, is the grazing angle or the X-ray? So the grazing angle of X-ray absorption is a great technique, but it's often done in air. So
yeah.
This could
So almost every analysis we're doing is we're doing in air. One thing I didn't mention, my grad student, Chip Leggett, who is going to give the third talk in this session, he's been working on the development of a vacuum chamber suitcase that we can bring from experiment to experiment. And that will allow us to do some things, but not everything that we want to do.
Okay.
Yeah.
This is a really exciting program that you've got going. Is there, first a comment, and I want to see if I saw that correctly. With your comparison of the irradiation and then the impact, the whole sequence, it appeared that the impact had more of an effect than the irradiation.
Yeah, which is not necessarily what we would expect from the remote sensing data.
Okay.
Yeah.
I mean, it could be any number of variables, but okay, so I got that
Yep.
impression. Second thing, is there any way, and I think the answer is probably no, that you can do the irradiation and the impact together?
That is a question we would have to work very hard with Mihai and Tobin and David James at Colorado to try to figure that out. I don't know the answer to that question, but if the answer is yes, then they would be the ones that would figure that out. Or maybe Tom. Maybe we could do it down in Georgia, right? Yeah, for a sec, yeah. Let's do it. It'll be great. Okay. Oh, sorry. Yes, Jack.
I reported at LPSC on the apparent shielding of some old regolith, 3.5 billion year old regolith at Shorty Crater due to the existence of a global magnetic field at the time. Its maturity index was like 8. And that suggested, compared to other maturity indices in the valley, that your dust or micrometeorite impact process was about 10% of the total maturity. That's just maybe a check later on when you get farther down.
So this is a really important point. This is something that's bothered me for a very long time. So I've spent some time thinking about swirls, as Carly and others know, and my perception of the swirls is that the magnetic shielding plays a strong role in the maturity or lack thereof of the swirls, and that would imply to me that the dust, or that the micrometeoroid bombardment, which is probably not affected by the magnetic field, probably doesn't play too strong a role in the maturation process. But it's not just my experiments here, or my group's experiments here, but plenty of people who are doing the laser shock experiments and other things that show lots of spectral changes and structural changes in the formation of nanophase iron with impacts forming. And so this is something that the laboratory community and the remote sensing community are going to have to start to suss out and understand. And sound like a broken record, just like everybody else said. If we could actually go there and get some samples from one of these swirls or one of these other magnetically shielded areas and bring them back, then we could, probably figure it out. And I'm preaching to a choir here.
Well, in effect, those samples at Shorty Crater,
yeah,
the
sure.
light gray
Those
regolith are a swirl sample in a sense.
Sure,
because it
that's a really good
appears
point.
like it was protected for most of that 3.5 billion years, or at least the essential part of it.
Maybe those deserve a second look.
Yeah, biomagnetic field. I think that explains what we've been talking about now here for a couple of years, because it's within the range of global magnetic fields that Weiss and others now are postulating. 3.5 billion years.
Okay.
Yeah.
All right. So we're going to have to move on. I apologize. We're already falling a little bit behind here, but this is a really fun discussion. So thank you.